Here we have a nice cubic map. The question is, A, what are the fixed points of that map? And B, what is the stability associated to those fixed points? So pause the video and try to come up with the answer. Fixed points are obviously points where f of x equals x. So what we need to do in our case is find the solution to the equation f of x, which is x cubed plus x equal to x. So that's a rather complicated equation telling us that x cubed should be equal to 0. And then after much hair scratching, we indeed figure out the solution, namely x is equal to 0. So 0 is the fixed point of the map. Good. That's part A taken care of. Let's have a look at the stability of that fixed point. So we know the straightforward way to calculate this is have a look at the derivative of our update rule and evaluate that at a fixed point, 0 in our case. So the derivative of x cubed is 3x squared, and then the derivative of x is 1. Now, if we evaluate that at 0, what do we get? 1. And that's a bummer, because the theorem that we would hope to use is valid if the derivative is strictly smaller than 1 or if the derivative is strictly bigger than 1. So here we have a conundrum. We cannot use the theorem. We have to be a little bit more creative and see if we can figure out for ourselves whether we have a sink or a source, a stable or an unstable fixed point. Let's first have a look at a very small perturbation. So we're sitting at the origin and we perturb it slightly to a positive value. So let's see what happens if our initial condition is a small positive number plus epsilon. If we have a stable fixed point, we will end up, after applying the map, closer to 0. If we have an unstable fixed point, this thing will run away further from 0. So what happens in our case? If we apply the map once, we get x1. It's going to be equal to the cube of epsilon, the positive number, plus epsilon. Now, compared to our original distance from the origin, epsilon, we now added a small positive number. So the end result is that this thing is larger than x0. Actually, we can see that this thing runs away from the origin, because we can keep on repeating that procedure and this thing will actually run away towards infinity, simply because we start from this number and then we add that number over here, which is positive. Can we do something similar for negative perturbations, just to have the complete picture? Obviously, the same thing is true there, as we can easily verify, because in that case, after applying the map, this cube will also give us a minus sign, and then we have minus epsilon. So also here we have the situation that this runs away. So this is the origin. We start from a small negative perturbation, and then after applying the map, we end up with something which is even more negative. So the whole thing just runs away towards infinity, away from the fixed points. So the conclusion is that the origin in this case is actually an unstable fixed point, a sink, a source rather, sorry.